Now let us see what is Raoult's law. According to Raoult, for a solution of volatile liquids, the partial vapor pressure of each component of the solution is directly proportional to its mole fraction present in the solution. Okay, this is the definition. For a solution of volatile liquids, we have taken a solution of two liquids, volatile liquids, the partial vapor pressure of each component. In the example, we have taken two components 1 and 2, component 1 and component 2. The partial vapor pressure of each component means P1 and P2. P1 and P2 or P1 or P2, partial vapor pressure of each component of the solution is directly proportional to its mole fraction present in the solution. You have taken mole fraction of component 1 as x1 and mole fraction of component 2 as x2. Okay, so mathematically, how to write this Raoult's law? See, for component 1, according to this Raoult's law, for component 1, P1, partial vapor pressure of component 1 is directly proportional to x1, that is, the mole fraction of component 1. Similarly, for component 2, partial vapor pressure is P2 and it is directly proportional to its mole fraction x2. Now here we can write using the partial pressure of pure component, we can write this as P1 is equal to P1 naught into x1. P1 naught means what? You know that. Partial pressure of pure component. Here P2 is equal to P2 naught into x2, where P2 naught is the partial pressure of pure component 2. So this is how you write Raoult's law mathematically. But according to Dalton's law of partial pressure, the total pressure exerted by the mixture of non-reactive gases is equal to the partial pressure of each gas present in the mixture. Here also we have two components in vapor phase, that is in gaseous phase. Now total pressure exerted by that two components is equal to what? The sum of the partial pressures of those two components. P total partial pressure or total pressure exerted by the component is equal to the sum of the partial pressures of individual components, that is P1 and P2. P total is equal to P1 plus P2. We know what is P1 and what is P2. Now you try to write P total in terms of P1 and P2. So P1 is equal to what? P1 naught into x1. P2 is equal to what? P2 naught into x2. So P total pressure is equal to P1 naught into x1 plus P2 naught into x2. Here we can write this total pressure in terms of partial pressure of any one of the component. You can write it in terms of partial pressure of any one component. You know that x1 plus x2 is equal to 1, or we can write x1 is equal to 1 minus x2. Here I have substituted, instead of x1 I have substituted 1 minus x2. So we can write this as P total is equal to P1 naught plus P2 naught minus P1 naught into x2. Here in this equation, look at this. This is a constant. At given temperature, P1 naught does not change. P2 naught is also a constant. This entire term, P1 naught is constant. This entire term is also a constant. So which is a variable here? x2. The mole fraction of component 2 is a variable. Looking into this equation, Raoult's law, in combined form of Raoult's law, we can make three conclusions. We can make three conclusions based on this equation. What are those three conclusions? The first conclusion in that is total vapor pressure over the solution, that is P total. Total vapor pressure over the solution can be related to the mole fraction of any component. Here we can write this P total in terms of mole fraction of component 2, or you can write P total in terms of mole fraction of component 1 also. For that purpose, you have to write x2 in terms of x1. You can write how to write x2 in terms of x1 using this equation you can write. So P total can be written in terms of x2 or in terms of x1. That is partial mole fraction of component 1 or mole fraction of component 2. So that is given here. total vapor pressure over the solution can be related to the mole fraction of any component. Any component, it may be component 1 or it may be component 2. Just while writing these two mole fractions in terms of 1 and 2, you use this equation. Next, second conclusion. Total vapor pressure over the solution varies linearly with mole fraction of component 2. This conclusion is based on this equation. I already told you P1 naught is a constant, P2 naught is also a constant. So which is a variable here? X2, the mole fraction of component 2 is a variable. That's why here we can write P total is directly proportional to X2. So it varies linearly with the mole fraction of component 2. The last conclusion is depending upon the vapor pressure of pure components 1 and 2, that is depending upon P1 naught and P2 naught initially at given temperature, depending upon the vapor pressure of pure components 1 and 2, depending upon P1 and P2 naught, P1 naught and P2 naught, total vapor pressure over the solution, that is P total vapor pressure over the solution decreases or increases with increase in mole fraction of component 2. So what is the meaning of this term? Depending upon the vapor pressure of pure components 1 and 2, depending upon P1 naught and P2 naught, total vapor pressure, that is P total, over the solution decreases or increases with increase in mole fraction of component 1, that is with increase in X1. Look at this equation. P total, I have written P total is directly proportional to X2 in conclusion 2. Now you look at this, X1 plus X2 is equal to 1. Now as you increase the mole fraction of component 1, as you increase X1, X2 decreases. As you increase X1, X2 decreases. So now P total also decreases. P total also decreases. As you decrease X1, X2 increases to making it equal to 1. X2 increases, P total also increases. Here P1 naught and P2 naught are constants. They are not going to change at given temperature. Now which is going to change? P total is going to change with respect to what? With respect to the mole fraction of component 1. It may increase or decrease. Say as you increase the concentration of component 1, that means when you increase X1 mole fraction of component 1, mole fraction of component 2 decreases because the sum is always equal to 1. It decreases. What happens when mole fraction of component 2 decreases? P total decreases. Similarly, when you decrease the mole fraction of component 1, that is X1, when you decrease X1, what happens the value of X2, mole fraction of component 2, it increases. What happens to P total? It increases. So that is conclusion number 3, which can be represented in the form of a graph. Here we can use a graph for explaining this conclusion number 3.